All right, so let's talk about the AI power ecosystem. Okay, let's talk about the hidden layer, what it actually takes to run AI. Because up to this point, we've been talking about AI as if it was a capability. We've been talking about it like a capability, which it is. But now I want to talk about it like a system because it's not just software. AI isn't just software, it's physical, it's expensive, it is resource intensive. And as of late, over the last year or so, it is being it has been heavily contested. And with all of the advancements, with all of the innovation, with all that they have been doing, it is still unstable. So, what I want you to understand is that with everything that you've heard about AI growth and opportunity and transformation, I want you to know that it's sitting on top of a foundation that is still being built in real time. And the reality is, if that foundation doesn't scale, everything above it slows down. And so, like I said, we look at AI as something intangible and it's physical, it's not abstract. Every response is produced by a real machine in real places and using real resources. It has to compute hardware through servers and GPUs. It requires physical facilities, data centers, electrical power, continuous supply. It requires cooling infrastructure, and that becomes heat management. It requires land, zoning, and construction. And what I want you to understand as we continue to move through this segment is that AI exists because infrastructure exists. Let's just strip away the illusion, right? When people say AI or the cloud, it sounds light, it sounds invisible, it sounds like it's floating somewhere. And that's not real. Every time you ask AI a question, that request is routed across networks into physical facilities where machines will actually process it. And these are not small machines, these are industrial size or industrial scale systems. These are racks of servers, thousands of chips, massive electrical draw, constant operation. And this is what I think most people don't realize. AI models, especially the large ones, they don't just run once. They're trained repeatedly. They're fine-tuned. They're served to millions of users simultaneously. And that's what I want you to understand. This is a actual physical action. So what you experience as a simple response is the result of a massive physical system working continuously behind the scenes. So let me say it like this. There's no such thing as just AI, right? There's hardware, there's power, there's cooling, there's space, and there's coordination. Now, here's why this matters, because every projection that you hear about AI scaling, right? It assumes that we can keep building more and more, and we can build more of this, more machines, more buildings, more power capacity. And the thing that I need you to understand is that that assumption is being tested now. That's why you may hear that they have plans to do A, B, and C with AI, and maybe a few weeks later, they retract that information as if they never said it to begin with, because it is a physical component to AI that, because it's not always present in the input, and by the time we get some of the outputs, we don't see what's happening and what's working behind the scenes. That's why AI is not limited by ideals. The ideals are there. We know how to get the ideals. We learn how to finesse the system so that we can get the ideals right now. But it's limited by infrastructure. Think about it like this. Think of AI like electricity. You don't see the power plant, but everything you do depends on it. And if the power plant can't scale, the system slows down. So now that we've grounded AI in the physical world, let's go inside the system itself. Let's get into the machine, what a data center really is. The space, the system, the coordinated system of compute power, cooling, and network that is needed in order for AI to exist. So let's take this a little bit deeper. A data center is not just a building with computers. It's a coordinated system. And everything inside it has to work together. So let me try to break this down. First, compute, right? So this is where AI actually runs. And increasingly, this is powered by GPUs. And that's not regular processors. GPUs are designed for parallel processing. And that means instead of doing one calculation at a time, it does thousands at a time. Because that's what AI needs. Now add memory and storage. Because these models are so massive, they require large data sets, weights, parameters, and immediate computations. Now add on the networking. These machines don't operate alone. They communicate at extremely high speeds with low latency connections and high bandwidth, because delays inside the system will slow everything down. Now, here's where it gets intense. That's where the power is. And these systems draw massive electricity. And not just from the grid. They require backup systems, generators, redundant power feeds, failover mechanisms. Because as we become more accustomed to AI, downtime is not acceptable. And so now, once you get to the power and the generation of that power, now we add cooling. And this is where people underestimate the true complexity of all of this coming together. Because all of this compute generates heat, and I'm talking about extreme heat. So now you need advanced airflows. You need those airflow systems. You need liquid cooling. You need water circulation. And I was listening to someone the other day, and they were talking about how some of these facilities are experimenting with immersion cooling. And that's where hardware is literally submerged in cooling fluids. Now, that just went all the way over my head. I don't understand it, but I know that they don't know enough to perfect that yet. But the thing is, if heat is not controlled, the system will fail. So what you have is not just a building. You have a synchronized, coordinated system of compute, power, cooling, network, and resilience. And they all have to work together. They're all working together to produce responses in seconds. And that's what you're interacting with. It's not just AI. You're interacting every time you're interacting with compute, power, cooling, network, and resilience. AI performance is not just about smarter models. It's about faster, more efficient systems. See, this is not an office. It's closer to a power plant mixed with a factory in a network hub, right? It's more than just, like I said, just AI. It's all of these things combined together, and it's enormous. It's massive. So now that you understand what it takes to run one of these, let's talk about what it costs. And this is why when people say AI is going to take my job, I'll say this: it might take one of your jobs, but trust me, a lot of companies will be hiring people back in massive numbers. I guarantee you. I guarantee you. All right. So the cost of AI is real. And scaling AI, it requires capital, it requires energy, water, long-term investment. It requires community alignment. Now we step into the real pressure point, right? The cost. The cost. Because this is where the story shifts from innovation to constraint. Because AI is not cheap. It is one of the most capital intensive technologies that we have ever seen. Or let me just say this, that I've ever seen in my generation. So let me break it down based on how I understand it. First, capital, okay? Building a modern data center can cost hundreds of millions of billions of dollars. And this is something that I was introduced to in my last function as I was doing IT audits. I realized that a data center, it takes so much. It requires land, it requires construction, hardware, infrastructure, security, networking. And that's just to build it. That don't even have anything to do with running it. Let's talk about running it. Because these facilities operate continuously. And that means that there's going to be constant power consumption, constant cooling, constant monitoring, constant maintenance. You take that and then you layer in energy. AI workloads are energy intensive. Think about it. When you train these large training models, they consume enormous amounts of electricity. Serving those models at scale continues that demand. So it doesn't go anywhere. Now, on top of all of that, add water, because cooling systems often rely on water, which means local water resources will be part of the equation. So now you're not just talking about technology, you're talking about energy infrastructure, you're talking about water access, you're talking about environmental impact. Now, here's the key connection. All the excitement that you hear about AI, all the projections, all the expectations, all of those are based on one assumption. And that's that they can continue to build and sustain the infrastructure at scale. But companies are now learning that scaling is harder than expected, more expensive than expected, more constrained than expected. And let me be clear, AI is not limited by imagination, because imagination is what got us here. It's limited by resources. And I'm going to pause from the material real quick and just share that I've been in I've been in IT for many years, and I have seen this level of excitement. I've seen innovation. I've seen organizations go down the rabbit hole. I've seen them go in one direction and have to pivot back, okay? So that's why I'm not so moved by everything that I hear about the potential of AI. I know how to work it, trust me. And I know that it can be beneficial. But I also understand that it takes much more than what they're telling us in order to compute through AI. This is why you're seeing partnerships between the tech companies and the energy providers, and why data center location decisions are becoming strategic. This is why your utility bill is going up. This is why you see protests in some of these rural areas that they're trying to buy a property because they need land. This is why you see communities and counties standing up to these big companies, and they're saying, you're not going to get into our water supply, right? So AI is starting to look less like software and more like a utility system that requires continuous supply. All that innovation you see is sitting on top of a resource-intensive engine. And that, as I understand, is not going to quickly change. Now, in the future, they may come up with some solutions for what we're struggling with now. But in the short term, long term, we're not going to see a lot of change with this. So now the real question becomes, what happens when the expansion meets the real world, right? This is what companies are faced with now. Because they had the ideals, they had, the plans, but now it's meeting the real world. And now they have to deal with it.